Okay, so for this first review video, we're going to talk about absolute value equations and their graphs. So first off, let's start with equations. So our first step is always going to be to isolate the absolute value expression. So we always need to get the absolute value bars completely by themselves before we can do anything. Next, we need to set up our two cases to solve. So we need to set up our positive case, which means that we just drop the absolute value bars and solve for x. So we don't change anything about the original equation. And then our negative case. So this is where we have to take the opposite of what's inside the absolute value bars. So say we have x plus 3 inside of our absolute value bars. What we're going to do is put a negative outside of those and distribute the negative in, and that's how we get our negative case. So we always have to check our solutions to make sure they work, specifically when there are variables on both sides. So if there's an x outside of the absolute value bars, then there's probably a chance that you're going to have an extraneous solution. So remember, an extraneous solution is when you find a solution, you did everything correctly, but it just doesn't work in the original equation. All right, so let's go ahead and start with number 1. So first off, I want to point out that we have this x on the outside. So we need to check for extraneous solutions. All right, and then we're just going to go ahead and isolate our absolute value bars. So that means anything outside of these bars, we need to move to the other side. So in this case, that would be that plus 4. So to move it, I'm going to subtract 4 from both sides. So we're going to have x minus 2 equals, and 2x and negative 4 are not like terms, so we're just going to write them next to each other. All right, I'm going to split up my cases now. So I'm going to make my positive case pink. So I'm going to do x minus 2 equals 2x minus 4. And we're going to go ahead and solve that one for x. So remember, your positive case is just literally dropping the absolute value bars, leaving everything the same, and then just solving. So I'm going to subtract x from both sides. So we're going to end up with negative 2 equals x minus 4. And then we're going to add 4 to both sides. So we're going to have 2 equals x. All right, so that's one possible solution. We will check it once we find our other solution. So I'm going to make my negative case purple. So now we need one extra step where we put a negative outside of what's underneath our absolute value bars. And the right side stays the same. All right, so we distribute that negative in, so that makes it negative x plus 2 equals 2x minus 4. And then we need to get all of our x's to one side and everything else to the other side. So I'm going to add x to both sides. Those cancel, and we have 2 equals 3x minus 4. And then we'll add 4 to both sides. We'll get 6 equals 3x. And then divide both sides by 3, and we get x equals 2. Again, so since we got the same number twice, we just need to plug it in once to check to make sure it works. So if it doesn't work, then we have no solution. If it does work, then it's just our only solution is x equals 2. So let's check. So we have x equals 2. I'm going to plug it back into the original. So everywhere there's an x, we're going to put that 2 instead. And this is something that you don't have to do by hand. So if you just typed it directly into Desmos, type the left side in and then the right side and make sure they both equal the same thing. So I'm going to go ahead and simplify. So 2 minus 2 is 0 plus 4 equals, and 2 times 2 is 4. Absolute value of 0 is just 0. 0 plus 4 is 4. So we're left with 4 equals 4. Make sure that's a true statement. We know that 4 does equal 4, so that means that our solutions are good. So we're going to go ahead and say that our answer for this one is 2. And you can see that written as x equals 2 or 2 in the curly brackets. Either way, just know that it's 2. All right, so for number 2, we're going to solve this, but right off the bat, I already know what the answer is. So whenever you see absolute value bars on a side by themselves, so they're already over there alone on the other side of the equal sign, and it's equal to a negative number, we know that absolute value can not be negative. So that means that we have no solution. So there's no x value that you can plug in that will give you a negative number. So we say no solution. You might also see this, which is just known as the empty set. So like there's nothing written in those curly brackets. So that just means no solution as well. All right, so we're going to go ahead and go to absolute value inequalities. So absolute value inequalities, we're going to follow the same steps we did before. We're going to isolate, and we're going to solve the positive and negative cases. So first off, and then we have to graph it on a number line. So it changes a little bit. And it depends on what inequalities we have. So whenever we have an open circle, that means that we have less than or greater than. So we don't have that line underneath if it's an open circle. And open means it's just not filled in. And a closed circle is going to be less than or equal to, greater than or equal to. Anything with an equal to, and that's going to be a filled in circle. All right, and then a little trick to remember is when to shade between the endpoints and when to shade outside of the endpoints. So if you have less than or equal to, then you're going to shade between the endpoints. And if you have greater than or equal to, you're going to shade outside of the endpoints. Okay, so I'm going to go ahead and make this because I think some people still struggle with this, which is okay. So this is a less than sign. And you can kind of tell because it kind of looks like an L. And then this is a greater than. So it's important that you know the difference between those. All right, so we're going to go ahead and solve some examples. So first thing we need to do is isolate our absolute value bars. So our absolute value bars are almost by themselves, except we have this 3 right here. So we're going to need to divide both sides by 3 to get rid of that. So we're going to have x minus 4 is less than 3. All right, so only now that we have it isolated do we split it up into positive and negative case. I'll use the same colors as before. So positive is going to be pink. X minus 4 is less than 3. We just drop those bars and then solve. So I'm going to add 4 to both sides. So we'd get x is less than 7. All right, then we need to find our negative case. So I'm going to do negative x minus 4 is less than 3. So let's distribute the negative in. We have negative x plus 4 is less than 3. And then we're just going to solve that like we normally would. So I'm going to subtract 4 from both sides. We get negative x is less than negative 1. And then because we have a negative x, we need to divide both sides by negative 1. And don't forget, when you divide by a negative, you have to flip your sign. So these cancel, you just have x. The sign has to flip to become greater than. And then negative 1 divided by negative 1 is 1. All right, so going back to our original problem for our graph, let's figure out what we're going to have to do. So we have less than. So less than tells us we shade between, And because there's no equal to, it's going to be an open circle. Okay, so we can label our number line however we want to. So we have our solution of 1. Just make sure it's in order from least to greatest. And then we have our solution of 7. So 7 would have to go on the number line. All right, and then we just graph it from there. So we're going to have an open circle on both of those, and we're going to shade between. So we're going to connect those open circles. And that's how we would graph that. Also, if we wanted to put this in interval notation, it's a lot easier to do it once you have the graph. So it would be from 1 to 7. And they would both be parentheses because they're open circles. All right, let's go to number 4. So we're going to isolate our absolute value bars first. So we have absolute value bars. We have this 5 minus on the outside. So don't forget that we need to subtract 5 from both sides. And this negative that we had stays in front because we haven't done anything with that yet. And then we need to divide both sides by -1 to cancel out that negative. So we have x plus 1 is greater than -3. All right, so here's where we can actually stop with this question. So anytime you have absolute value bars greater than a negative number, that tells us that our solution is all real numbers. And that's because we know that absolute value bars are going to give us a positive number no matter what. So it's always going to be greater than -3. So if we wanted to graph this, we're just literally going to do the entire number line. And what that would look like in interval notation would be -infinity to +infinity. All right, and then final one for inequalities, we're going to follow the same steps. So we're going to go ahead and isolate our absolute value bars. So subtract 9 from both sides. We have -2 x plus 3 is less than or equal to -2. Divide both sides by -2. And we end up with x plus 3 is greater than or equal to, because we had to flip the sign, 1. All right, so then we drop the bars and we solve. So we're going to do x plus 3 is greater than or equal to 1. And we're going to solve that for x. So subtract 3 from both sides. We get x is greater than or equal to -2. All right. And then for our negative case, we're going to do negative x plus 3 is greater than or equal to 1. Distribute that negative in, so we get negative x minus 3 is greater than or equal to 1. So negative x, if we add 3 to both sides, would be greater than or equal to 4. And then we have to flip the sign because we're going to divide by that negative, less than or equal to -4. All right, so if I put this on my number line, I'll put -4 here. And then we'll put -2 here just to keep it spaced out. All right, so let's go back up to our original problem. And we're actually going to look not here to figure out how we're going to shade. We're going to look here. So since this is greater than, that means that we're going to shade outside of the endpoints. And it's equal to, so it's going to be a closed circle. All right, so we're going to go ahead and put a closed circle on both of them. And shading outside means that we're going to draw outside of them. So they don't get connected, they're disconnected. All right, and interval notation for this, since we have an arrow going to the left, it would be -infinity to -4, and then union -2 to infinity. All right, and you can also, if you're taking the SOL or if you're working on the final exam, you will have the Desmos graphing calculator. So you could just type these directly into Desmos and it will solve them for you. So save your time, especially if you're on the SOL. You could just do this on Desmos. You can at least use it to check your work. All right, so for number 6, we need to write the inequality based on the graph. So we have open circles and we have it shaded between. So what I'm going to do is I'm going to just write my x right above the number line. And then because it's between, we know -6 is this way and 2 is this way. And we're just going to fill in our inequalities. So we know that x has to be greater than -6, which is how we would read that, and x has to be less than 2. And x has to be between those two numbers. So that would be our inequality. Okay, so now we're going to go on to graphing. And with graphing, we need to know what our parent function looks like. So remember, our parent function is the absolute value equation with no transformation. So just y equals absolute value of x. So for our graph, I'm going to use -2, -1, 0, 1, 2 for our x values. You can use anything. That's just usually what I use because it's like the center of the graph. All right, and what we're going to do is figure out what the y values are. So we do that by plugging them into our equation. So if we plug them into the absolute value of x, -2, the absolute value of -2 will be 2. Absolute value of -1 is 1, 0, 1, 2. So we're going to put those points on the graph. So -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And we know that those should be, like it should make a V shape once we connect them. Okay? So let's kind of figure out what our basics are for the parent function. So our domain, we have an arrow on the left side of our graph and the right side. So domain should be all real numbers. And that's true for all absolute value graphs. Our range, though, we're going to have a restricted domain because we have this point right here where our graph doesn't go past. So the lowest value in our range would be 0. And we'd have a closed, or we'd have a square bracket because that point is included on our absolute value graph. And then we have arrows going up forever, so it would be to infinity. All right, increasing and decreasing. So increasing, or I'm going to just start from the left side of my graph. If I trace this, I'm going down as I trace. So decreasing would be that left half of the graph. It would happen from -infinity, because remember we use x values, and it stops at 0. And we always use soft brackets when we're doing increasing and decreasing. All right, and then we're going to start again at that same spot that we stopped. And that's our increasing. So that would be from 0 to infinity. All right, and then end behavior, both ends are going up, so that would be infinity and infinity. So we have arrows on the right and the left going up, so we know that they both have to be infinity. Okay, so for the rest of these, I'm going to show you how to do them by hand, but you can also use Desmos for this kind of problem if you're taking the SOL or the final exam. So first off, based on the inequality, we need to know if it is dotted or solid, shaded above or shaded below. So because we have a less than symbol here, that's going to be shaded below. And because there's no equal to line underneath it, it's going to be shaded, or sorry, it's going to be a dotted line. All right, and then it's important to know our transformations. So that +2 on the inside moves our graph to left 2, and the +3 moves it up 3. So I'm going to go ahead and graph that first point, left 2, up 3. And because there's no vertical stretch or shrink, then our slope of this graph is still just 1. So the parent function slope is 1, so is this one. So we're going to go up 1 over 1, up 1 over 1, and do the same thing mirrored in the other direction. Okay, and we're going to dot our graph. Put your arrows on the ends. And we said it needs to be shaded below. So that means we're going to shade underneath that V. We're going to shade the lower parts of it. So we would shade that whole area. And again, if you were to type this into Desmos, you would see this exact graph. Or you would see a different graph and you can tell that you did something wrong. All right, and then for number 7, we have this symbol. So that means we shade above because it's greater than, and it's going to be a solid line. Okay, something different that we have now, we have this negative 1/2. Whatever number is outside is our slope. So negative 1/2 tells us that we have a vertical shrink of 2 and a reflection over the x-axis. But for the sake of absolute value graphs, it's kind of easier to think in terms of slope. So we also have this -1, which moves it right 1, and the -2, which moves it down 1, or sorry, down 2. All right, so always graph your vertex first, so that would be your right 1, down 2. So I'm going to move from the center, move to the right 1, and then move down 2, and that would be my vertex. And then from there, we can just use the slope to get the rest of the points. So because the slope is negative 1/2, I'm going to go down 1 over 2 from that vertex point. And I'll do the same thing in the opposite direction. And you can continue until you get to the end of your graph. Oops. All right, and then we're going to connect. So remember, we have a solid line because of that greater than or equal to. I'm going to do my solid line. And then we're shading above. So I'm going to shade this whole top area. So we're above the absolute value graph. All right, and then the last two are just writing the equation given the function. So this is where you definitely need to know your transformations and your parent functions. You can type this kind of thing into Desmos once you get the equation and make sure it matches the original to check your work, but Desmos really can't answer this type of question for you. So first thing we're going to do, we need to find any transformations that happened, and we want to find the slope of the line. So first off, think about your vertexes being at 0, 0. And we move that vertex to the right 2. All right, so we move right 2, and then that vertex moved up 1. All right, so last thing we need to do to write the equation is to check the slope. So I'm going to go from that vertex point on the graph up to like the next perfect point. So if we go up 1 over 1, that's what we're going to do for this whole line. So the slope didn't change at all, so we have no vertical stretch or shrink. So slope is still 1. All right, so then we just fill that into our equation. So we have y equals absolute value of x. The right one makes us go -2, and then the up 1 makes us go +1. And then you would want to type that into Desmos and check to make sure it matches the original graph. So trust your gut, but also check your work. All right, and then for the next one, our vertex, again, we're going to move and see we move to the left 3. And we moved down 1. All right, and then we need to check our slope. So if we still start at that vertex point, and then we go to the next perfect point, we're going to go down 2 over 1. So our slope would be -2 because we went down. All right, so if we write that equation, then our equation would be y equals, the slope goes out front, so -2, absolute value, x +3 because of that left 3 and then down 1. Okay, so that's basically the gist for absolute value. So definitely a lot of this you can type into Desmos to check your work, or to at least, if you're completely lost on a test, you can use it to answer, maybe. All right, but you're done with